Good morning, everyone. My name is Elizabeth Crawshow, and I will be presenting on a portion of my project that I'm currently working on at the University of South Carolina. I started this project over the summer, and I am gratefully able to continue working on this project and finish it. For this portion of the project, I'll be reviewing the size analysis of the catalyst that we created. As an overview of this project, we wanted to study particle sizes using chloropatanic acid with forms of ZIF8, which is a meta-organic framework with different surface areas and pore sizes. We tested a series of this derived MOF, and we wanted to increase the pore sizes and test this hypothesis. Why we decided to choose a MOF? Well, for starters, MOF hasn't really been used as a support for a catalyst. But moths are highly porous structures with a large surface area, so we wanted to see if we could build a catalyst out of it and see what the size of the particle sizes were. The goal behind the small particle sizes is with a small particle sizes, that means there's less platinum needed for the catalyst and therefore makes catalysts in general cheaper. So like with your catalytic converter, if you need less platinum, then the converter would be cheaper. So this here is our table of samples that I had used. I'll refer to them as MSA, MSB, and MSC. With also their point of zero charge, which is used for the type of synthesis that we used, and then we also had our surface areas. So a breakdown of experiment is we wanted to adsorb CPA onto the carbonized MOFs by means of strong electrostatic absorption, or SCA. SCA exploits surface chemistry by inducing a surface charge to electrostatically absorbed ionic metal precursor complexes onto the support. This is done by exploiting what's called the point of zero charge, which is where your positives and negatives, they even out. And so the idea behind it is if you have a high PCC, which is a pH level, then you want to change the solution of your catalyst and what you derive your catalyst into a lower pH, and then the vice versa for a low PCC and a high pH. So our experiment consists of different shaker times and pHs, which is shown on the table. We decided to do different amounts of shaker times because when we originally did an uptake survey, which essentially what did was we were able to find the most optimal pH. We also noticed that with your different time ranges, there was a really slow diffusion rate, so you had a higher amount of platinum on the support with a 24-hour than you did on a 1 hour. So we wanted to see what those kind of particle sizes look like. And then we also decided to compare it with a high pH and a low pH, because we did notice that with the 24-hour, it increased the most uptake was with the higher pH. These samples were analyzed using XRD after the synthesis to study the particle sizes, which is what I will be reviewing. So to start off, I wanted to review the MSB XRD results. I wanted to go over this one first because this is most similar to that of what the control kind of looked like. We used aluminum C as the control. So essentially here you have your platinum 111 peak, and then you have your 200 peak, and then your 220 peak. And so the way that this works is that with the sharper peak, you're going to have larger particle sizes. And our physically mixed control sample, which is this top line right here, shows what the platinum particles would look like if they were large. And it shows about what was like the maximum size that the XRD can be. And then down here at the bottom is the support, which we use to compare these peak sizes to. We also decided to use a dry impregnation, which is the more common way to synthesis. And it does make larger particle sizes than SCA, but they're a good way to compare particle sizes. But as you can see with these different platinum peaks, that there weren't really any peaks in the first place, which means that the particle sizes are extremely small. And we were able to luckily use the share equation to determine an estimated particle sizes based off of peak size, because you could see that there's like here, there's somewhat of a peak, and here there's somewhat of a peak. And then this sample here had a pretty large particle size, but that's because that there was a sharp point. This here had a small particle size because it is a more broad peak, and the more broader the peak is, the less sharp, the smaller the particle size is. This here was our MSA results with our different peaks, which were very non-existent. There are absence of crystallinity within all the samples, which indicates very small nanoparticle sizes. And we ended up doing our physical mixture twice because there were no peaks at all, so we wanted to see what was going on there. We were also unable to successfully use the share equation due to those extremely small peaks because they essentially look absent and that there were no peaks in the first place. Moving on to the MSC results. This was more normal, like what we had with our MSB. We did have a little bit of a contamination over here, but our peaks did show. And our physical mixture is showing like what the maximum particle size will look like, with a small particle sizes for your dry impregnation, and then with absent peaks for all of the other samples, which we also were unable to successfully use the share equation due to these really smaller absent peaks. But this is a great thing because the smaller the peaks are, the smaller the particle sizes are. So in summary, we were able to use SEA on these metal organic frameworks. And these XRDs showed very, very small particle sizes, but we're going to do some further analysis, so some future work. We're going to analyze using scanning transmission electron microscopy, so we can actually measure that diameter of the particles. But I wanted to give thanks to everyone, and a great thank you to the University of South Carolina for hosting me, for NSF for funding the project, and just for USF for letting me continue staying on the project, and for working with the different professors here. These are my sources, and thank you.